I want to introduce you to Dr. Nicholas Nordendale. He has extensive finite element analysis experience. He used to work for Abacus or Dassault Systems, and he also has applied fracture mechanics to a number of applications across the industry. So I thought it would be a great idea to invite him as a guest and have him guide you through the fracture mechanics concepts using NASGRO, which is one of the software that is being used in industry to assess the fatigue crack growth. So, Nicholas, can you hear me over there?
Yes, I can.
All right. So I pass it to you. Thank you for allowing us to come into our show and showing us how to do this.
All right. Well, thanks for having me. As Vinay said, my name's Nico Nordendale, and I'm going to go through some examples of how you use NASGRO, which is a commercially available software to basically do calculations, to calculate things like stress intensity factors and to predict how cracks will grow given known material properties about how cracks grow through that media. So as you see on the screen, this is what pops up when you open up NASGRO. Now within NASGRO, there are several different modules that you can open that will do different things. For example, you can look at NASFlaw, which is fatigue crack growth. You can look at NASSIF, which is a calculator to calculate what the stress intensity factor is of a given geometry and a given applied state of stress. You can use NASCCS to calculate critical crack size. Probably the most common module within that is NASFlaw, which is going to allow us to pick a geometry, material, and applied loads. And from that, it'll be able to iteratively predict how the crack will grow through those applied loads, either until it completes all the loads or until it reaches some form of failure, either through net section stress failure, which would be an actual strength failure, or crack that breaks through a given geometry, or the really concerning failure modes, which are unstable crack growth or a stress intensity factor that exceeds a critical value. So we'll go ahead and if I click NASFlaw here, this module here will open. I'll just move this over to the side. So this module here is NASFlaw. And so the first thing that's going to pop up is going to be a selection for how to pick which geometry you want to look at. So if I open this, there are lots of different types of geometries you can look at. You can look at a through crack, you can look at corner cracks, embedded cracks, or some of the most common, which are surface cracks. Surface cracks are what we would typically think of as a semicircular or semi-elliptical flaw that starts on the surface and moves into the bulk material. So let's look at one of the most common cases. This is called SC30. Surface crack iteration 30 is a semi-elliptical surface crack with an offset in a plate. And you'll see here, this diagram shows you what the calculator is going to use. So some applied stress, S0, some applied moment. Here is the crack front with a known depth A and a known width 2C. And you have the ability to apply a constant stress, or you can apply varying stress through your net section. You also have the ability to offset the crack. And these calculations here kind of show the geometric limitations. Basically, NASGRO is a compilation of lookup tables. There's tons of material data as well as calculations for the shape function. If you remember back to your equations of what stress intensity factor is, it is your stress times a geometric factor times the square root of pi times your crack size, or pi a. That shape function is what varies as a function of your geometry. So the width, the crack location, the thickness, all of those slightly change the calculation for stress intensity factor. And a lot of researchers over the years have compiled that into peer-reviewed journal articles and textbooks. And so NASGRO compiled all of those. And so those calculations only exist for certain conditions. So for example, you can see here that the crack depth divided by the thickness has to be between 0 and 0.95. If you try to input values that violate this, NASGRO will abort and tell you it can't calculate values outside of that. Let's go ahead and select this very common
Hey,
surface crack.
Nico, before you go forward, can you describe a little bit what approaches you use to come up with which geometry is the best for your situation? Like, how do you think about that? Could you tell us a little bit about that?
Sure. So first of all, it's probably most common that uh, you want to look at flaws either because you have observed a flaw existing in a certain part that you're looking at, or the type of manufacturing that you're doing is likely to lead to those type of flaws being generated. In metal parts, one of the most common workmanship sensitive processes that can be done on metal parts is welds. And welds are typically more likely to generate flaws because it depends on whether or not a manual welding process is being done through a welder or it has a machine that's doing the welding. Either of those cases, the weld is there's variability from weld to weld as you do go through manufacturing. That's more likely to have a flaw in it than, let's say, plate material or forged metal parts, which have much more process controls in place in order to make sure the manufacturing is repeatable and forms a nice polycrystalline material. So welds are very commonly generating surface flaws, and so that's why in most industrial applications, there are some forms of non-destructive evaluation like X-rays, dye-penetrant inspection, eddy current inspection, magnetic particle inspection. All of these different inspections allow for us to either do surface detection, like visual or dye penetrant, where you just smear a dye over a surface and then you use like a black light in order to make that dye kind of pop out at you. Or if you're using things like X-ray or ultrasonic inspection that can go through a solid, those are called volumetric inspections, that can detect things like embedded flaws, things that exist inside that wouldn't exist on the surface. So typically, there are standards, depending on the industry, whether it's aerospace, aircraft, automotive, marine, there are standards that will stipulate the type of non-destructive evaluation that you have to do in order to detect flaws and the typical limitations of those techniques for how small of a flaw can they reliably detect. So for things like dye penetrant inspection can only detect the surface. And so if I'm looking at a plate, something that doesn't have a variation in geometry if you look at my cursor in that direction, if there's no variation in that direction, then a plate is appropriate. If I was looking at a tube or certain type of pressure vessels that have some curvature to it, curvature can have an impact in the geometric factor of the calculation. And so it might be more important to look at something like a semi-elliptical surface crack in a hollow cylinder that's axially oriented or that's circumferentially oriented. There are many options for how depending on the geometry that you're looking at. So this kind of just shows for surface cracks some of the types that you can use. For any consideration where if you think that the part is big enough where the geometry isn't really going to affect the solution near the really localized stress intensity at the crack front, then SC30 or SC01 are the most common ones that are used typically in practice. So let's say you select a surface crack and you have these requirements here. First step is usually the simplest. It's just to input what your geometry is. So let's say we have a plate that is a thickness 0.1 inches. And if I want, that's the thickness here, T. Now I'm going to input the width. And I'm going to make this large enough to where it's not going to impact what's going on at this crack tip. So I'll just say that this is 10. And if this is a centered crack, B is just half of W. So I'll say this is 5. Now, depending on the version of NASGRO you have access to, some versions have implemented the NASA standard based on NDE. If you have an older version of NASGRO, I think it's earlier than version 8, this option isn't there. So you have to input these manually. But essentially, the way this works is you have a depth A, and then you have an A over C, which describes the shape of that crack. If A over C is 1, then A is equal to C, which means that the crack is perfectly circular. If you do a smaller A over C, it may become more elliptical, where the length or the width of the crack is actually longer than its depth. So if this is 0.1, let's say that this is an appropriately small flaw that's maybe 0.01 inches. And we'll start with something straightforward, and we'll say the crack is perfectly circular. And we'll say 1. And so there's some other options here that kind of go beyond the basic use of NASGRO, so I won't touch any of those right now. But that's all you really need to do at a bare minimum for inputting of the geometry.
Hey, Dr. Nordendale.
Yes,
So as an example, I know this looks like a plate, but say you have a cylindrical tank or some tank of some sort, like a fuselage.
Mhm.
Is it true that I can still use this solution procedure because I could approximate it by the width being very large? Is that correct? Like, I can look at it from that perspective, use this simplified geometry for a more complex situation like a fuselage tank?
Yes, definitely. And in fact, I would encourage that mostly because there are, as you saw, some of the other options that I put in here. There was SCO4 and SCO5, which are for flaws in some type of hollow cylindrical structure. Those geometries do have limitations here that control the thickness of the fuselage compared to the radius. And so something as large as like an airplane fuselage or a launch vehicle diameter, something that's that large, in those particular cases, where something like thin-walled pressure vessel equations would apply, or even just in the case where that radius compared to the thickness is too large, those geometries might not actually be applicable. So in those cases, the curvature is so slight compared to the size of the flaw. And in this case, we're looking at a flaw that's 1/100th of an inch in depth. So a radius of curvature of something on the order of 70 to 80 inches, feet of radii, that curvature would have negligible impact on the geometric factor. So it's a really good point. So after you're done putting up the geometry, you would then go to the material. So the simplest thing to do is, if you know the specific material that it is you have to look at, is to simply click this button to show material list. Now, NASGRO is a really great compilation of strength and fracture and the fatigue crack growth properties as a database. And so there's a lot of different materials go on here. And so let's just look at a common aluminum. Aluminum is really common. So those are all going to be under here, 1000 through 9000 series aluminum. And from here, you can see which series you want to pick. So one of the most common aluminums you probably see is 6061. That'll be under 6000. You'll see that there's 2 of them here, and you'll see there's a dash T6 or a dash T651, depending on the heat treat you want to look at. T6 is pretty common, so I'll look there. From here, oh, go ahead.
Yeah, Dr. Nordendale, I wanted to see if you could also comment on being careful about, have you had the situation where you have to be really careful about what you're selecting? Sometimes something may look close enough, but may not be the right option. Could you comment on that a little bit?
Absolutely. So in practice, these are good numbers to start with, but in any case where in practice I had to use this to be involved in an anomaly investigation or disposition of a hardware nonconformance, something really important, every single time I would run these by a materials science expert to verify that the strength, the fracture toughness, the crack growth parameters are all accurate and or bounding of test data of the hardware it is you're specifically trying to look at. So all of these properties will get you, close. So if you know the material is 6061 T6 and you're sure that's the heat treatment, then you're in the right ballpark. But from here, you can see really closely that the first one is a plate or a sheet, where you have LT or TL or just longitudinal transverse or transverse longitudinal and lab air room temperature, versus something that's extruded. And you see these different extrusion directions. This one is also a weld. So these will change the parameters that you're looking at. And all of these parameters, all the properties come from actual ASTM tests that had to be performed under the rigorous ASTM standards to make sure that they're valid. And enough samples have to be generated such that you have an appropriate statistical significance in those values. Even still, whenever you manufacture parts, whenever you have hardware that's built, the raw stock of the material will come with material certificates of conformance, which come from the actual like the forging houses or the metallurgical houses that provide that material. They have to provide that data that shows, yes, this aluminum meets these requirements. It has these minimum strength, elongation, fracture toughness properties that at least make sure that you're analyzing to the correct values. So for this particular case, if I just click on these values and I say, okay, a number will pop up. Something of note, you'll notice that at the beginning of all of these, there are letters and numbers. That's because when I click OK, a specific material code will exist for this particular material, and that code will be M6AB13AB1. That is a unique material code that is useful in industry, because if I'm an analyst and I'm working with a analyst from a different company or a government agency like NASA or the Department of Defense, if you're trying to validate each other's work and make sure that, like, if, for example, I do an analysis and I want to make sure another engineer can get the same results, reporting what that material property is can guarantee that you're using the same one. Because all it would take is me to have accidentally clicked extruded instead of a plate sheet, and the code would change. So it's a really good way to double check that you're using the correct material property. So if I say OK here, this will autofill all of the properties. And you'll see, just like I just said, material properties ID is right here, M6AB13AB1. And here was the name that comes along with it. Now, I'm not going to get into all the details of this. You can go through the NASGRO help manual if you want exact explanations of all of the parameters. But some of the most important ones are the first four. This is ultimate tensile strength, yield strength. Then you have K1E and K1C, where these two are fracture toughness. This is a fracture toughness in a plane strain condition, and this is fracture toughness in the plane stress condition. These parameters have to do with the strength, or not strength, but the fracture toughness increase that you can achieve when you go from a plane stress to a plane strain condition, or vice versa. C and N are your crack growth parameters, where DADN equals C times delta K to the N power. P and Q are transition coefficients that have to do with how your crack growth parameters accelerate or decelerate in zones 1 and zones 3, which I'll show you in a minute. And you have a few other parameters that I'm not going to get into much here. As far as failure mode, a good practical use is to make sure that at least these first two are usually checked. And this is where, as you cycle through your loads that you'll define in the next page, it will always check the stress intensity factor and the net section stress that is being calculated in front of your crack. And it'll check that against these properties that you've defined. Whichever hits first, which stress intensity factor that exceeds your fracture toughness, or a net section stress that exceeds a term called your flow stress, and your flow stress is the average of ultimate tensile strength and yield. Whichever one goes first is what leads to failure. Now, it's important to know that in practice, you should know that NASGRO is still just a calculator that needs an intelligent engineer to govern what it's doing. There are some cases, depending on the material that you're using, the geometry that you're using, there may be cases where the net section stress may exceed your flow stress, and you, the engineer, might decide that that's acceptable. What that means is that your part is yielding. Now, if you're only yielding at a tiny part in front of your crack tip, that may be acceptable if that just means that your load redistributes. You know, we know in if something you had like a pressure vessel or a tank, that may just mean that there's a tiny region in your surface that's yielding and the load will redistribute around. That may be acceptable. In that case, with great discretion on your part, only if you understand the physics of what's going on, you can elect to uncheck that. So it will no longer flag a failure in the solution when it gets to that. Now, if you have something like a beam or a strut or a bolt that has a minimum cross section and it's a single point of failure, you don't want to suppress that check. You want to make sure that you're checking, hey, have I gone above what this is capable of withstanding, and this from a strength perspective? So general good practice is to keep those both checked. And if you're curious about what this data looks like, you can click this box here and this little window will show up that basically allows you to plot what the DADN curve looks like. And there's some titles and limits you can set here, but if you show the default, it looks like this. So this shows you actual test data with the actual curves that are being used. And you'll see here, these are all the properties that exist right here. So all these exist up here. And you'll notice for this case, there are 3 curves. And your curves are for an R of 0.75, 0.5, and 0.1. R is your alternating stress ratio. Basically, it's a ratio that looks at the loads that you're applying, which we'll look at the next tab. Basically, you're going to have a different amount of crack growth if you cycle from 0 to a peak stress and you go up and down from that stress-free condition all the way to peak stress. That's going to cause a different amount of crack growth than if you start at, let's say, something like 50 KSI and you cycle up to 80 KSI. Going between 50 to 80 over and over and over again is a different amount of crack growth than going from 0 to 80. That's because your mean stress, which is your maximum minus your minimum divided by 2, that number is different. So NASGRO has different R ratios embedded within the software to make sure that whenever you put in a load block of varying levels of stress, it picks the correct crack growth for that case. Now you'll notice what the plot is DADN versus delta K. Delta K being from your minimum stress to your maximum stress in a given cycle. You have 2 different stress intensity factors, the minimum stress and the maximum stress. That delta stress intensity factor is what would be used in this calculator. Let's say you were given a total delta of 10. If your R was 0.1, it would go up here. And this is the amount of crack growth that you got from just that one cycle. So that's part of what makes NASGRO really powerful, is that the calculations that it's doing at any one time isn't particularly difficult. The fact is that if you have a long enough stress history of cycling through a lot of different stress cycles, through lots of different amplitudes, that's really time consuming to try to manually keep track of. So NASGRO allows you to really easily input what those are and iterate over and over and over again until it finishes the load block that you've defined or until it predicts failure. So,
Dr. Nordendale, one more question. If I have my own data, right, and my coefficient n, where it says 2.3, my test data said, I think it's more like 2.2. Is it possible to change that number, or I have to create a new card altogether?
good question. So you can change these as you see fit. If I say 2.2, you'll notice at the top comes up with a warning saying the parameter values have changed from their original material file values. So you can change those, and if you change them significantly enough, these curves will start to deviate from the test data. Now, if you have your own test data, you can certainly use these to plot them against your own test data to make sure that you're getting the correct values. And there are other cases that may be used to change that. For example, if these are the minimum values, but if you know from the certificate of conformance that come from the metal houses that maybe the minimum yield strength is actually something like 43, and that's been confirmed from test data, you can change those as well. So, you're free to change these, but just be aware that making those changes is going to deviate from the test data that has been, calculated from actual ASTM tests. So also be aware that when you are done making these runs, you have the choice to save your files. If you try to reload those files, NASGRO will always ask the question, if you've changed these properties, it'll ask you by default, do you want to use the values from NASGRO, or do you want to use the values from the input file that you changed? So make sure you know which ones you want to do. If you aren't paying attention to the dialog boxes that pop up, you might accidentally reload a file and have it default back to the NASGRO values instead of the values that you put in. So that's all the minimum you need for the material. The next part is the load blocks. So there's multiple ways to handle load blocks, but fundamentally, keep in mind, first of all, that you need to note what units were being used. You'll note these are all in imperial units or English units, but these are obviously not in PSI. The yield strength of aluminum 6061 is not 41 PSI, it's 41 KSI, or kips per square inch. So that means whatever load blocks you put in also needs to be stressed in terms of KSI. So if I wanted to apply a single cycle of stress, you'll notice there are two sets of stress. There's S0 and S1. To know what those are in any given geometry, you need to go back to the geometry tab and see what the options were. S0 here is your tension stress. S1 in this particular case is the moment, or your bending stress. So if I were to assume that this plate is only being subjected to tension, and if I assume it's going from a equilibrium state of 0 to a total stress, obviously we can't exceed the flow stress, which is the average of this, so that'll be 43.5 or 43. It needs to be some stress below that. So if I were to say this is 30 KSI, if it was all tension, then these would be 0. You can either type these in as 0 or you can leave them be. The last thing you have to do at a minimum is your scale factor. Now these values for S0 and S1, these are multiplied by these values. So some people may choose to go 0, 30 and put this value as just 1, but it would be equally equivalent to make this 30 and make this 1. There's no mathematical difference between the solution for that.
Dr. Nordendale, could you comment a little bit about units, being consistent with the units?
Yep. So, as I was saying, the thicknesses, all this information here was being input in inches. And that has to be the case because, as I said, these are in KSI. Now, there are options here where you can see what those units are. So right now, by default, I'm using inches, inch per cycle, kips, KSI, KSI square root inches. Those are what's being used. You can very easily change to Newton, megapascals, millimeters. You can convert back to, I don't think there's actually a default option for straight up SI. I think a lot of that is because they're trying not to make these digits too significantly long. But make sure you check what those units are. Like I said, by default, NASGRO is going to open up in imperial units with stress in terms of KSI. So you need to make sure that whatever load blocks you put in here are in terms of that. I'll show you an example after I finish this one where the actual values may not be stress. In some cases, like with pressure vessels, the scripts actually give you the option to apply the load, the pressure load, directly instead of actually knowing what the stress is, which could be useful. But for this particular case, you can see from this geometry, tension stress is S0 and bending stress is S1. Now you'll notice it says S0 at T1 and S0 at T2. That is your min and your max. So your min stress and your max stress in terms of your cyclic stresses. Now in this is just one particular cycle. So if that's all I wanted to do, and I'll come back and show you how to add cycles to this after go ahead.
And Dr. Nordendale, just to make sure, right? So one cycle is from 0 to 30 back to 0, right?
Correct. It's a full reversal of the load. Or I'm sorry, it's a full amplitude. So if you look at a sine wave, it goes from 0 all the way back. So the next tab is a build schedule. This allows you to do things like if you know what the service life is of the hardware that you're trying to design, there may be requirements per your standards that say, hey, you have to show that your part can survive 2 times its service life or 4 times or 10 times. This allows you to kind of customize what that is. Maybe if there's multiple rows here of apply 1 cycle of this, you could apply 10 cycles of some other amplitudes. You can kind of build that up here. The easiest way to do repetition is to just put an arbitrarily large number here. You can go all the way up to just south of 10 million if you wanted to. So as it is, if I leave this alone and I make this just 1, when I run this, it is literally going to apply 1 cycle from 0 to 30 back down. Now, that's going to be the end of that solution. And if it survives, it'll tell me what the new flaw size is from that. So if I wanted to save that and run it, it's just 1 button. Now, if you want to save it as an input file, you say yes, and it'll give you an option to type that in. That opens there. So you could put an input file name here. Save. And these are the results. So this is just showing you in a window what the results are. There is a separate file that gets opened to save your output. There's .output files that will save all these results. But you'll see here the final results, it'll say critical crack size has not been reached, which means 2 things. First, it means that your peak stress intensity factor did not exceed either K1C or K1E. It means that your net section stress did not exceed your flow stress. It also means that you did not break, this crack did not grow through this thickness. Now, it did grow a very small amount. You'll see, remember the original crack size was 0.01. The new crack size from 1 cycle is 0.0105. 0.00004. So that means the crack only grew, what, 4 times 10 to the 1, 2, 3, 4, 5, 6, 7. So the crack growth was extremely small for that one cycle. Now, it's very easy to make changes to that. Let's say I wanted to see when this crack actually did something interesting, either broke through or goes unstable. So I might just increase this some arbitrarily large number of times. Now see, now from that, it says again, critical crack size has still not been reached. That means that this crack can be cycled 10,000 times from 0 to 30 KSI, and this crack has still not gone unstable. Now the crack has grown quite a bit more. Instead of the original crack size of 0.01, the final crack size is 0.015. So we're getting close to crack growing a more significant amount of the depth.
I have a question there. So, is there a way to? I think there's a way to plot the crack size with number of cycles, but also to plot the K, the stress intensity factor with number of cycles, so I know how close I got to the critical value.
Good point. So, easiest way to do that: crack size versus number of cycles. You can click crack size and say plot versus n. And if I say show plots, it'll show you here. So this shows you from 0 to 10,000 cycles what the crack size is. Now, you'll notice there's 2 curves here, A and C. That's because if you come back and, it's not gonna let me do that. If you come back and you look at your geometry, you remember the crack is growing in 2 dimensions. It's growing through the thickness, or in the A dimension, and it's growing through the width, or the C dimension. So whenever you plot these, it's useful to know which one is growing faster. In this case, you'll see the crack is growing faster through the width. Now, does that mean it's going to go and unzip, or it's going to go unstable in that direction first? Maybe, but chances are, in this particular case, A will break through the thickness probably before C goes unstable. So that was how to plot crack size. You can also look at the max K, or the max stress intensity factor. If I look at that as a function of n, this shows you here. Now here, this shows you what we just saw illustrated, is the stress intensity factor in the A direction is smaller than the stress intensity factor in the C direction. So yes, given enough time, and assuming the thickness of our part was thick enough, eventually the stress intensity factor in the width dimension would go unstable first. So that was a simple case of just showing how to cycle a single stress amplitude. Typically, it's not so straightforward. Typically, we might say, okay, there's one case of going from 0 to 30, but there might be 100 cycles of going from 5 to 15, or there might be 1,000 cycles going from, let's say there was a compressive stress. Compressive stresses do different things at the crack tip. So maybe this was -10 to +10. As I said earlier, your R ratio, which is again, looking at the DADN curves, there's different crack growth depending on what your load block definition is. All those different load blocks that I just showed you had different R values. And so it's going to be different crack growth as it goes through those. So if this is now my service life, this is what the part is going to experience. Now, if I try to run this, See, this runs pretty quick. So it still made it all the way through without rupturing. But you'll notice that this number, or the schedule number, is now different than the total cycles. The schedule number is defined as this is a single load block. And when I went over here, I repeated it 10,000 times. So if the total number of cycles is what? 1,101 for a single schedule. So 1,101 times 10,000 should be this number here, 11,010,000. So by the end of 11 million cycles, or 10,000 schedules of this load block, this is the final crack size. So lots of interesting thing happening. And if I wanted to look at what that crack size looked like for this case, you'll start to notice something more interesting happening. So what you see happening here is that this is relatively constant crack growth. Well, you'll notice that at some point, things start accelerating. Crack is growing more and more and more as it continues on. And part of the reason for that is that even though the load blocks are being repeated, the crack is growing. And if the crack is growing, the stress intensity factor is changing with each calculation.
So in that plot, I do want to comment, if you can bring the plot again, that typically, let's say in an aircraft design, you will have intermediate inspections. And so the flaw may be growing, theoretically, it could grow from 0.01 to 0.014, and you can go back to the field and inspect it right at that point, and then you realize, oh, the flaw didn't grow that much, so I can readjust my analysis so that the crack size corresponds to the inspected value in the field. So this is just a prediction. Is that correct, Dr. Nordendale?
Exactly. Yeah. These are all based off of, nominal properties. It's standard in fracture analysis that you apply what's known as a scatter factor to your results, because the results are so they're so heavily influenced by the input properties that the tiniest changes in like those values of C and N can drastically change your results given enough cycles. And so that's why typically, if you know what the service life is, you typically have to analytically show that you can survive several times that schedule just for a typical baseline design.
Yeah, and Dr. Norton, I want to point out too that that factor can vary from industry to industry.
Agreed.
So, for example, in the launch vehicle industry, the factor could differ from the aircraft industry. So, as you go through this, it's important to understand the requirements for your program, or whether you're working on aircraft, and what are the assumptions that you're using for that particular design you're analyzing. Is that correct?
Exactly right. So, yeah, it's very important that you understand not only what the scatter factor is, but like you said, the initial flaw size. I kind of mentioned at the very beginning of how do you decide what the geometry of your flaw is, and I mentioned that typically it's one of two things: either you're analyzing a flaw that was detected, and so you know the size of it, and that's what you analyze to, or you are assuming that flaws exist in your hardware at a smaller size than what you can detect depending on your detection methods. If you're doing an X-ray, standard X-ray equipment has a resolution that goes so fine. And if, luckily I have the newer version of NASGRO, and so I can actually look up what some of those are. If I were to do dye penetrant inspection, dye penetrant per NASA standards has actually said the smallest flaw that dye penetrant can reliably detect is a 0.025 deep flaw. That is 0.2 in the A over C. So that is the smallest flaw that that method can reliably detect. So that means you have to assume that there are flaws smaller than that exist, because you can't detect it any more reliable way. So that becomes what I assume my initial flaw size is. And typically in a lot of industries, we assume that that exists in the worst case location of the part and the worst case orientation. So if you have a finite element analysis or a hand calc that tells you, okay, I know what the highest stress or the peak net section stress of my part is, I'm going to assume a flaw is oriented at that location such that that stress is going to open that crack. That is the typical standards across multiple industries that we see in order to perform fatigue crack growth calculations.
So another question, Dr. Nordendale, if I didn't have, if the NASGRO version that people may not have this initial flaw option, is it correct that they could go to the NASA 5009 standard, or they can go to some other type of document like an ISO standard that could have this type of information?
Yes, so those are exactly right. So NASA standard 5009 or different ISO standards do outline what the standard minimum detectable flaw sizes are for various standard NDE methods, and those were developed across a lot of different, a lot of different industry experts and their experience for what are reliable methods. And different companies and different contractors buy this equipment to perform non-destructive evaluation, and most of those industries, whether or not they're radiographic machines, eddy current, ultrasonic, all of those different types, have their own internal standards to make sure that they can reliably detect smaller flaws. So those are the two ways in which we typically initiate what that flaw size is. We indicated here how to cycle through these in order to see crack growth. Let's see what happens if we want to actually get some crack acceleration to the point of failure. So I'm increasing this value to be very close to the yield point, which means I'm already pushing this very close to failing pretty quickly. So right there, things change this time. So as you look through this, here are the results. So you'll see it's checking two things, as I mentioned. It's checking fracture toughness criteria, and it says, hey, no failures predicted. But it's also checking net section stress, NSS criteria, and it says failures imminent. So basically what it's saying is, because this crack is growing through this thickness, as it grows through the thickness, this ligament or this remaining material is changing. Now remember, stress is a pressure divided by a cross-sectional area. And so what it's looking at is it's looking at this net section in front of this crack. And as the crack grows, the stress is actually increasing. So basically what it's saying is, hey, this remaining ligament is getting so small, the stress is increasing, it's about to fail. And so the final result is, it says right here, net section stress exceeds flow stress. So this, if you were to say, could this fail from unstable crack growth or from strength? The answer here would be strength. This was not a stress intensity factor failure. This was basically, it was predicting a yield or a ultimate strength failure. And the final results are failed at schedule number 5350, which means it was in the middle of the 5,350th repetition of this load block when it failed. And this was the number of cycles that it survived. So if your boss or your instructor or anyone were to ever ask, how many service lives can this part safely survive, or how many safe lives does it have, it's this number minus 1. It safely got through 5,349, and it failed on the 5,350th cycle or of repetition of that service life. So
And
that,
then we will apply the factor of safety or some sort of scatter factor to that number, right? To that particular number.
so that's an interesting point. So I've seen multiple industries treat it somewhat differently. In general, the scatter factor typically says something like you must demonstrate that your part can survive, X number of service lives. Maybe it's 2 service lives, maybe it's 4, maybe it's 10, maybe it's somewhat larger number. To me personally, the most straightforward way of comparing this is saying, let's say I needed to survive 10 iterations of my service life. The easiest way to deal about that is say 5,350 is greater than 10, instead of trying to do a division of it's not so straightforward to write a margin of safety. The reason is because fundamentally a margin of safety calculation is a extrapolation of how much capability you have left in a linear sense. But we saw that if I look at, let's say, max K, I plot that versus N, this is not linear. So I can't, saying I have margin of safety, if, for this particular case, if I were to go and calculate this as, 5,350 divided by 10 minus 1 is the standard margin of safety calculation, then this would imply, okay, I have 5,340% margin. But this plot right here shows different, because that would imply I have that much capability left at that same level, which would draw a straight line across here. But as you get closer to the end of life, things rapidly deteriorate very quickly. So my personal opinion is it's much more straightforward to simply, report these numbers as either exceeding or being less than your required number of service lives. So 5,350 is greater than 10x, then it's past the requirement. If the requirement was, 6,000 lives, this is less than that. And so you'd say, okay, it doesn't pass the requirement. So that's kind of a quick run through of all the minimum steps in order to get a NASGRO run through. All the rest of these options here, you can do things like this. So right here, what I just did is I said, hey, tell me what the actual, in a tabular form, tell me what the maximum K value is as it cycles through. And you'll see here 2 columns, K calculated in the A direction and the C direction. You'll see right now, this is what? 4.7, 5.3. And as the crack grows, these numbers grow. Your stress intensity factor goes up as you cycle through.
So it's the same data. It's the same data as the one that we plotted, but in tabular format, right?
Correct.
Okay.
Yep. And same thing. You can look at your crack size as well. It's going to show a similar trend. Your crack size accelerates as it moves through here. Now, if you go to your textbooks or your online references, they're going to basically break down your DADN curve into 3 regions. And those are basically division. If I was going to look at just the blue curve, something probably starting around here is where you have zone 1. You have some, basically some crack initiation region where it's starting to grow. And then from here to the end of the linear portion, that is region 2. And that is sometimes referred to as the linear crack growth region. Some people call it the Paris region, where it follows Paris law, which is DADN equals C times delta K to the n power, which you should know is just a line in a log scale, where C is the y-intercept of this graph, and n is the slope. Once you get above K1C, that is when you have gone unstable. That's when you get into zone 3, which is unstable crack growth. So that's when, if you ever see unstable crack growth, it's basically saying, hey, this thing is getting away from you, it's going to unzip at that point. All right, so that is all the basic information that you need in order to run NASGRO.
Th-
Go ahead.
I was going to thank you for really going through everything here and providing your expertise so everybody can learn. And I hope that from these examples, you have learned how NASGRO can be used successfully to solve fracture mechanics, flaw growth types of analysis. One thing I do want to mention is that you don't need NASGRO to do this kind of analysis. If you have the fatigue crack growth and you have the geometries, you can then, for the particular situation you have, you can integrate the equations yourself and calculate the crack growth behavior. But this type of software makes it more handy because it has all the intelligence built in so that you can then use the software and leverage it for your application. Finally, this software has been developed by SWRI, and you can get it from them as well. But the primary thing here is that, as any software, it is sort of a black box. So bad input in, bad output out. Dr. Narnado, do you have some final lessons learned on that aspect, like using software such as this one in a way that can actually come and hurt you if you use it incorrectly? And then with that, we'll close this particular aspect of this NASGRO tutorial.
Yeah, definitely. So one of the things that I learned by, making simple mistakes and having them kind of come back and be revealed is through test data. So as I mentioned, there are a lot of, material properties that are here, and very small changes in any one of them can drastically impact your final result. So whether or not you use nominal or average properties, or whether or not you use some type of statistical minimum like A basis, B basis, S basis, some minimum 3 sigma properties in order to protect you from that statistical variation, will drastically impact your solution. There are cases where using minimum properties might tell you you can only survive a minimum number of service lives, but in reality you can survive far more because you have safety factors to account for those. So it's important as engineers to think about what your safety factors cover you for. In a lot of fatigue crack growth, we apply scatter factors to the number of service lives that you have to demonstrate you can survive, and that scatter factor is particularly to cover the material variability. And for that reason, it's typical in multiple industries that you actually use nominal or average properties in your fracture instead of minimum properties. So that was a lesson that I had learned pretty early on. Other lessons that were actually really useful, I'll just kind of mention it really quickly. One of these, I think SCO4, this was a case that I had learned early on. So this is a surface crack in a, like a pressure vessel, a hollow cylinder. In this particular case, there are multiple ways in which you can apply the stress. In one case, it actually lets you apply the stress in a discrete way where you can basically say, hey, at X equals 0, the stress is maybe 1, but at X is 0.5, we're talking 0.5 through the thickness, the stress is less. And all the way out at the surface, the stress is, even less. So you can apply these discretely, or you actually can apply S0 from unit internal pressure. One of the lessons that I learned from that is that when you check this box, it changes what your input is in your load blocks from the stress to actually just giving what the actual pressure is. So in that particular case, I thought I was supposed to be putting in the stress directly, but I wasn't reading clearly enough that what it's asking for is the pressure value itself. So if the pressure in this tube is 500 KSI, or not KSI, 500 PSI or 0.5 KSI, I should not put in the hoop stress or the axial stress, PR over T or PR over 2T. That's the actual stress that is felt by that pressure. And if you check this box, you're supposed to only put the actual pressure value. It will calculate the stress for you. So that was a case where I kept putting on I kept putting in the pressure or the stress value, not realizing I was putting in the wrong thing, and the part kept instantaneously failing because I was an order of magnitude overloading the structure.
So is it correct, Dr. Nordendale, that I could potentially do some hand calculations too to verify stuff? For example, instead of running this whole thing, crack growth analysis, maybe I go to the left-hand side, that's module where it says stress intensity factor solutions, NASGRO on the very left. And perhaps I just do a quick calculation to compare, right? Is one approach, because you don't want to get into a situation where you use the software, you don't know what's going on, and then you mistakenly provide wrong solutions to your design team.
Very good point. So yes, so this was NASGRO, which all it's doing is it's calculating your stress intensity factor. So because of that, some of this looks similar, but instead you'll see here you're just applying the basic geometry, the basic stress, and for that the only inputs you give is the yield stress, because it doesn't need to know there is no crack growth in here. All this is doing is the simple one calculation: K, delta K equals delta sigma times the shape function times square root of pi a. That's all this is doing. And this allows you to put in different flaw sizes, and when you input those, the output will be the stress intensity factors. So I encourage the use of hand calcs here to make sure that the values you're putting in are on the correct order of magnitude what you expect. If you put in values here and you get a stress intensity factor that's way higher than your fracture toughness, that's going to predict instantaneous failure. So if that's not what you actually expect happening, or if that's not what you're seeing happening in practice, that's a good way to verify if what you're doing is correct. So that's a really good point.
Well, we thank you again, Dr. Nordendale, and please keep safe out there. And we will continue with the finite element tutorial on how this could be applied for fracture. So thank you very much, Dr. Nordendale, and have a great night. Now we're going to go, now that we went through the NASGRO tutorial, I would like us to go through the finite element demonstration with LIFU